Hello, this is Piotr Przybietin. In this video I will present the basics of the Chart program, which is a numerical version of the Molière chart. The program generally operates in two systems, the Carrera system, which we currently see on the screen, and the Molière system, which, well, I personally prefer and work with. However, between these two systems there are basically no differences in the analysis on the chart itself, but they do differ in the technical matters regarding the axes and so on. Generally the program also works in both the metric SI unit system and the imperial unit system. However, for me the SI system is also the default system. Okay, what we see on the screen is generally a complete analysis conducted on the Molière diagram, psychrometric chart. Consequently, we start by creating a new file. And now, regarding the general features of the program. The program is built in such a way that in this here place we have a window showing air parameters dependent on the cursor position on the screen. Here we have a window with defined points. Here we have a bar that allows us to define various predefined air transformations, as well as any point or directional coefficient. The given transformation in the form of the epsilon coefficient or the SHR coefficient. We have a process list button. We have a button for the list of created coefficients, and we can create a report here. Meanwhile, with this window we can very quickly, without entering the main settings of the program, change the atmospheric pressure. We can also decide whether we want the processes shown on the chart to be animated or not, as well as which values describing the given process should appear during the animation. Should it be only the airflow or also total heat, sensible and latent? And with this slider we set the animation speed. Here we have a button showing this top bar of the section with section photos, which allows us to describe transformations in a more readable way. Okay, here of course we can change the position of this window to any position if we're interested in it. To change the axis range we can use these buttons here, or the scroll. Here, if we use the scroll, we can decrease or increase the range of this graph. We can also change it here with these buttons. At the bottom we have analogous buttons here, and here to increase the moisture content. You can also do it if we venture generally into some distant areas of the chart that let's say don't interest us, and we don't want to later fiddle with buttons. We can simply press the default size button and return to the default range of our and the screen that covers 50 degrees Celsius and moisture content of 25 grams per kilogram, which in most cases during the analysis on the psychrometric chart is completely safe. Maybe I'll say a few words about the settings. Here we have a dedicated button where we can enter atmospheric pressure, or in the form of giving the value of pressure in pascals, or altitude above sea level. Here, if we enter a value, say 1000 meters above sea level, the program automatically calculates the appropriate atmospheric pressure for this altitude. But generally we work on, here the values are 1013 hectopascals, at least as far as I'm concerned. Next we have here the range of the graph. Basically we set it up here with these buttons, more conveniently in my opinion, for what we want to be visible, like the ISO line of relative humidity, density, enthalpy. Later some visual aspects related to displaying here these various windows. here we have where we want the description of the point to be located, as well as descriptions that are to be added by the point, and of course the color of individual lines, as well as the thickness. I suggest setting these thicknesses the way I have them. For example, the color, the thickness of the process is 4, that the slope of the line, and the thickness of 0.2. However, the others, meaning the lines currently shown on the graph, can be set to a thickness of 1. Okay, and now we can move on to declaring, for example, the first point in the nice chart program is very simple, because all you need to do is hover anywhere on the screen. This is of course the first way, observing the parameters here in this window, and we can define such a point. Of course, this is made easier for us by that cursor of ours, which shows us the intersection of all the lines. So it is convenient in that we can do it relatively precisely. We can also, of course, help a little with the scroll and zoom. And we click on the screen and name this point. And we confirm. Okay, here when selecting, we can of course still define where we want the description to appear. What if we don't know something? We can use hints by using the help button. If we have the first point, these functions will be inactive, because there have to be at least 2 points defined on the graph to do this. So okay, we press OK, and now we can of course create a second point in a similar way, or we can use a predefined process here. Let me show you how it looks for now, without, let's say, any deeper physical meaning. A transformation defined in any way. If it were a cooling transformation, it would definitely aim here towards reducing temperature and lowering absolute humidity. So I will click here at this spot, define the second point, and I assume the creation of a process with a previously defined point. Here I input the airflow or the mass of this air. I confirm with OK, and immediately on the screen, as you can see, the air transformation appears. Here automatically also appears a table with all the transformations we will define. And also here we have this transformation created in our table with the list of processes. If we wanted to edit such a transformation, for example, the amount of air, then we have to use this function by clicking on such a transformation, or double clicking on it to enter editing, or with the right button and selecting edit transformation from the menu. Okay, and in this case we have 1000 meters here. Let's assume we change it to 2000 cubic meters per hour, and here everything will automatically be recalculated also to just as it should be. We can also edit such points in various ways. The first way is simply to hover over such a point, grab it with the left mouse button and move it, observing in the window with our parameters some place that let's say interests us. Let's say it's here, for example. Of course this is all automatically recalculated. As I said, here we can select what we want to be animated during the transformation. Here we also have the speed of this animation. If we want such an animation to stop, we can simply move the slider all the way to the end, and then the animation freezes. Alright, as I said, here we have the ability to define various processes. Let's start by defining, for example, a point. Let's call it point 3. And set the temperature of 20 degrees and 50% humidity. This is another way of defining a point. Here also we choose where we want a given description to be placed. We can also choose if we want, for example, to capture a point on an existing line, process transformations, or also if we have a defined slope coefficient of the SHR line or epsilon, we can also place it on this line, or we can define a process immediately with previously defined points. But let's say that for now we are only defining another point, and it appears here for us. Okay, if we want to define the transformation differently, we can also go here, that is into the transformation list. We can click define transformation here, choose for example 2, 3, load the first point, which is 2, load the second point 3, set the airstream and confirm, and this way we have two transformations. Alright, now I'll show how to define a transformation using these predefined transformations here. Okay, so let's take for example a heating process. If we have no point defined, in this case we must define it first. So let's assume we will have the first point with a temperature of -20 degrees and 100% humidity, and we confirm. Okay, it appears here. Now we load it, and now we want the air from this point 1 to be heated, for example to a temperature of +20 degrees. So we enter that we heat to +20 degrees. We set the airflow here. For example, this is 2000 cubic meters per hour. Of course, we have two options to choose from. We can either set the temperature and the program will automatically calculate the required heating power, or we can set the heating power and the program will then calculate to what extent this heating power will be enough, to what temperature we will be able to heat this air. If we have any doubts, we can always use the help button here. It will open a YouTube video showing how to maintain it. Create. Here we just calculate, and we see that to do this we need 31.04 kilowatts of heating power, and the resulting point will have a temperature of +20 degrees and a relative air humidity of 4.4%. All that's left is to draw it on the chart, and here of course we can also zoom in if we need to. Here we can also use it if we were presenting our results to someone in this way, by clicking here. Here we click here, for example, as an inlet, or maybe not an inlet, but here, sorry, it's a heater. We press, and here we have, for example, here we have a room, for example. Okay, the remaining transformations in the form of cooling, mixing, humidifying, and drying are defined in a similar way. Here we have, for example, the possibility to define cooling based on the SHR coefficient, or using the surface temperature of the cooler wall. We always get a button under each such process definition showing how to use such a transformation. So moving on, we can define cooling using the bypass factor BF. We can define the adiabatic cooling transformation. We can define the mixing point based on 2 points, and the degree of mixing. We can define the transformation of humidification using steam at 100 degrees. We can define the transformation of humidification based on adiabatic humidification using water. We can define drying using cooling, that is condensation drying, and we can define drying using adsorption here as well. We also have here the function of defining the slope coefficient of a line. We can do this either through the epsilon coefficient, which is expressed by the ratio of total heat and weight and mass water gain, and it is expressed in kilojoules per kilogram. or we can also express the slope as the SHL coefficient, that is the so-called sensible heat ratio, expressed as the ratio of sensible heat to total heat. Okay, and that's briefly, generally one could say, the basic functions of the program. Here I might add how we can edit individual points, as I may not have shown that. We can edit a point by hovering over it and using the right mouse button to bring up the menu, for example, clicking edit point, or similarly in this window by hovering over the point. We can do an edit point, Alright, but that's just, but what I showed is only a part of the functions in the Xchart program. The real advantage of the Xchart program is the ability to automate drawing all air transformations on the chart. For this purpose, we use an air handling unit calculator, which is here, directly connected to the psychrometric chart. And here we can perform calculations for both winter and summer. We'll conduct a sample calculation for summer. I've already entered them here to save some time. We'll take a rotary heat exchanger. In this case, we can also define moisture recovery, which we won't do. Here we simply provide the parameters of the intake air. Here we provide the efficiency of recovery, the heat recovery section. Here we provide the degree of air recirculation in the mixing chamber. We provide the supply parameters after the cooler. In this case, we will be performing dehumidification, which means deep cooling to a temperature of plus 12 degrees. Here we enter the temperature of the cooler's surface. In this case, I enter 7, and as it says here in the hint, if we have a cooler with direct evaporation, in this case, we enter the evaporation temperature of the refrigerant. If we have a chiller, in this case, we enter the arithmetic average between the supply and return temperatures of the coolant from the chiller. Next, we set the temperature that we want to achieve after the secondary heater, the airflow supplied to the room, the airflow exhausted from the room. Here we immediately receive information when defining these types of parameters about how much total heat gain, sensible heat, latent heat and moisture we will remove from the room using this air. We also receive information about the SHR coefficient and its corresponding epsilon coefficient, and in this case it's enough to just press the plot on chart button, and all these transformations will be plotted on the chart without using this bar or predefined transformations. Let's just adjust it a little bit, and as you can see, everything has been drawn. For better orientation, we can describe it here using our icons, which I am doing right now. We can of course present this in the Carrier and Molière layout. Here we create a report from our analysis. As you can see, we have defined all the points, all the processes, transformations our chart presented, and a legend describing all the terms that have been used in such an analysis. We can also save it to a PDF, of course. And that's generally everything about the general features of the psychometric chart. However, the chart itself and the Xchart also have many built-in tools that facilitate the work of every engineer. Here, HVAC, here, which we can use. And now I would like to briefly present and discuss them. I won't particularly delve into this topic here because these tools have been described in separate video episodes dedicated solely to these modules. I so wiem, let's start with calculator R. Pressure losses. This is a tool with which we can perform calculations of pressure losses Ventilation systems are rather simple because it is quite tedious in certain circumstances. However, if someone wants to have control over each fitting, they can certainly use this calculator. This calculator is based on ASHRAE standards for calculating both local and linear resistances. This completely coincides with each other. An additional function is also the ability to calculate the attenuation of the given fittings here, as well as their own noise, self-noise through the fittings. So what else do we have here? What else do we need to do? Define the length, define the diameter of such a fitting, enter the flow rate based on which the airflow velocity is calculated. If we are dealing with an unusual fitting, or let's say there could be something in the fitting that constitutes additional resistance, we can enter it directly here in the form of pascals or using the local coefficient. Local resistances, the program can basically calculate resistances for any kind of material of such ventilation ducts. We can define this, or we can specify the roughness coefficient of steel or PVC material, or as I mentioned, I wanted to use any other material. We just need to define its roughness coefficient. The program also calculates the mass of both insulated and non-insulated fittings. If we want to calculate the mass of an insulated fitting, we only choose the type of insulation material. We set here the thickness of such insulation. The program has a built-in database here. Dedicated density of such a material is used, so it calculates the mass of the fitting by itself. However, if someone has more unusual values, they can of course define them independently, and based on that the program calculates the mass of the fitting, as I mentioned. We can accept this and it will automatically appear here. This module is generally connected to the acoustic calculations calculator, and thanks to it, it is possible to calculate the attenuation of ventilation fittings, which is later used in acoustic calculations. But I will show that on another occasion. However, the way to use the calculator is described in a separate video, which we can watch by clicking on this button here. Next we have a simple air balance calculator, where for a foreign user outside the territory of Poland, only this function is somewhat helpful. It is the determination of the amount of ventilation air based on typical, perhaps based on the nature of the room. So here you just need to ask the dimensions of the room, choose the type of that room. The program will itself indicate an approximate amount of air that should be used for ventilating a given type of room. These are literature data in Poland. However, for a user from Poland, we can also use two additional remaining functions based on our local regulations here. Here we have a calculator for re-regulatory elements. It is a feature allowing the calculation of pressure drop. What will be generated at here the damper or the axisymmetric diaphragm, if we are dealing with the necessity of performing hydraulic regulation of the installation, and we have to we determine a certain amount of pressure loss on some branch. With this module we can determine the opening angle of such a damper or the size of the axisymmetric orifice. Here we have a calculator for ventilation units, which I showed, and which is very a helpful element of the psychometric chart. Here we have a calculator for swimming pool holes based on the VDI 2089 standard, which is the German standard. Unfortunately, in Poland, we do not have any method used or defined that has the status of a standard or law. So we have quite a lot of these methods, which can be quite troublesome. However, most companies here offering pool systems are based on the VDI 2089 standard. So here we can also calculate any type, the swimming pool hole, considering the type of pool, various parameters of water attractions, wet floors, checking the ventilation conditions by eye to avoid condensation, and so on. Next we have an acoustic calculation calculator. As I said, this acoustic calculation calculator is actually connected with the pressure loss calculator, where by introducing the pressure loss of individual fittings into the calculation, we can later copy it to this calculator. And if we were to define, for example, some acoustic parameters of fan, fittings, silencer, and so on, and we do the copy, then they will be filled in here automatically. Of course, we can also do it manually without using that tool. However, in the calculator, we are able to calculate precisely what level of acoustic pressure, which is what actually interests us, will be established at a certain distance from the noise source, in this case from the diffuser inside the suspended ceiling. We input the dimensions of the room, the distance from the noise source, the coefficient, here the sound absorption coefficient, which depends on the finish of the given room, the directivity factor, which depends on the position of the element generating noise in the room, and we can in this way determine what the final sound pressure level at a distance R from this noise source. In this module we also have the ability to calculate the summation of noise sources, because it's not algebraic summation but logarithmic. This often causes some difficulties. Here we can do it very quickly in the program. Similarly, we can also, for elements placed outside, determine what the sound pressure level will be at a distance R from this device. We only need to define its sound power level, the distance at which we want to calculate, and also choose the option for the directivity factor. So whether we calculate this noise in open space, or if there are any obstacles along the way that will reflect and thus can cause overlapping on. And smaller restrictions of attenuation. This is important because engineers often face the problem of having to determine some level of sound pressure at a distance from the property boundary, so as not to disturb the noise, not to disturb the neighbor's peace, that kind of thing. Next we have a calculator for gains, heat and moisture from some surface, where we can hypothetically assume that we have in our facility, let's call it some kind of tub filled with water, and we want to calculate we can use this tool to calculate the heat from such a tub. Likewise, we have a tool here for calculating heat and moisture gains from people depending on their activity and temperature. Next we have an energy consumption calculator. This is the second, probably the most important element of this program, where we specify, we choose a city, one of 5,003 cities in the world, other parameters, work schedule, and we can quickly calculate how much energy a given ventilation unit will use, how much carbon dioxide it will emit. However, I will not focus on this because it has been described in under a completely different video, which is available under this button. We also have a great tool for calculating and optimizing the thickness of ventilation duct insulation, along with checking the conditions for condensation outside or inside the ventilation duct, depending on the set air parameters outside and inside the duct. Here there's also a separate video available that we can watch. And generally I would like to end on that note. Here I invite you to download the program, check its capabilities, and I think this tool is really very helpful for every HVAC engineer. Therefore I invite you to take a look. Thank you for your attention and see you in the next episode. Bye.